Hi everyone, I'm Shouvik Choudhury. I'm a distinguished postdoctoral fellow at the Academia Sinica Institute of Astronomy and Astrophysics in Taipei, and I mostly work in neutrino cosmology. And my collaborators are Steen Hannestad and Thomas Trump from Aarhus University, Denmark, and Nilay Bostan from Denmark in Turkey. And I'll talk about neutrino self-interactions in cosmology. So this talk is based on the following papers. The first two are written with Steen Hannestad and Thomas Trump, and the last one is written with Nilay Bostan. So the first part is related to the Hubble tension, and this is based on this paper, which is quite well received in the community, and it has 70+ citations. So I'll start with introducing neutrinos. Neutrinos have three mass eigenstates, which are quantum superpositions of three flavored eigenstates. And from neutrino oscillations data, we know all the masses must be different, and at least two of them are non-zero. And tightest bounds on the sum of neutrino masses comes from cosmology. And in cosmology, we usually use the approximation where all the masses are equal. It's called the degenerate hierarchy. And the reason is that cosmology is sensitive to the total energy density, which is proportional to the neutrino mass sum, but it is not sensitive to the individual masses, at least given even futuristic data. And the neutrino energy density in the early universe is parameterized by n effective, which basically gives the effective number of relativistic degrees of freedom. So in this paper, we have updated the constraints from cosmology on flavor universal neutrino self-interactions mediated by a heavy scalar of mass more than 1 kilo-electron-volts, so that we can take an effective 4 fermion interaction limit, because the CMB temperature is close to 0.3 eV, which is much less than the KeV range, so that we can consider this scalar to have decayed away. And then we can use this interaction Lagrangian Gij nu I bar nu j phi, where Gij is simply a diagonal matrix. And since we can write it as G delta Ij, then it's basically same in the mass eigenstates, in the mass basis and in the flavor basis. So the effective self-coupling G effective, if it is larger than Fermi constant, which is the coupling strength of the weak interactions, then the neutrinos will remain interacting with each other even after decoupling from the photons and baryons at a temperature of 1 mega-electron-volts, when the weak interaction rate becomes lower than the Hubble expansion rate. And this self-interaction rate per particle gamma is G effective square T nu to the power 5, where T nu is the neutrino temperature. And so basically neutrinos don't free stream until gamma becomes smaller than the Hubble expansion rate. This changes the gravitational potential in the early universe, because neutrinos don't travel at the speed of light and go ahead of the photon and baryon fluid. So neutrinos do not put the gravitational pull on photon and baryons. So basically the anisotropic stress is suppressed, and that changes the CMB power spectrum. It enhances the power spectrum, and it also causes a phase shift. And introducing this kind of interaction had shown potential in solving the Hubble tension in previous works in the very strong interaction range of G effective close to 10 to the power 9 of G Fermi, using older data. So the cosmological model of interest is this Lambda-CDM, which is a 6-parameter model, plus log G effective plus N effective plus sum of neutrino masses. And Kreis et al., which is this paper is a Princeton-Harvard Caltech collaboration, which is a very famous paper, and they found there's 68% bounds of log G effective at a pretty strong value, pretty high value. And with that strong interaction regime, they found H0, which can solve the Hubble tension, and N effective close to 4, which is basically the reason why you can solve the Hubble tension in this model, because this model allows you to get to high N effective value, which is not possible usually when you don't have interactions. So N effective and H0 are positively correlated, because N effective increases the expansion rate in the early universe, and that increases H0. So solution to Hubble tension came from very high and effective values of 4, which is one extra radiation species. But the paper used Planck 2015 low and high multiple temperature data with lensing combined with BAO, and they found similar goodness to fit to the data as Lambda-CDM, but Planck polarization data was not used in the main conclusions. So with the public release of the Planck 2018 likelihoods, we thought it is timely to test this model again. We made runs which incorporated the full prior range of log G effective from -5.5 to -0.1. And the posterior of log G effective is actually bimodal. So we have a moderately interacting case, which is basically a limit to Lambda-CDM. And then we have a strongly interacting mode, which is completely separate from the moderately interacting mode. And this mode is what gave a solution to the Hubble tension. And we also run the non-interacting case to compare with these two modes, so to understand the effect of the G effective parameter. So So what we find, if you see the lower left plot, which is the one-dimensional posterior distribution of log G effective, you clearly see that there are two modes for all the dataset combinations that we have tried. And the thing is, the left mode is basically the moderately interacting mode, and the right mode is the strongly interacting mode. And due to the phase shifts in the CMB power spectrum, this strongly interacting mode creates a completely separate mode in theta MC as well. And theta MC is basically the angular scale of the sound horizon, which is one of the most well-constrained parameter in the whole of cosmology. And the thing is that this is one of the unique features of this model, that this model can only this model can do is create a completely separate mode, which is 5 sigma away from the Lambda-CDM like mode in the moderately interacting case. So, and this log G effective parameter also has degeneracy with NS, and in the next slide you will see that log G effective is actually higher. This strongly interacting mode actually creates lower NS values, which is important for inflationary models. But the main thing in this plot is basically the plot for the 1D posterior distributions for N effective and H0. You can see that black curve, which is for temperature plus low multiple polarization data, and you can see that a large range of N effective is allowed when we only use the temperature and low multiple polarization. But as long as we use the high multiple polarization data, the blue and the red curves, then you can see that the polarization data is much more sensitive to N effective, and it does not allow values more than 3.5, and hence, and since N effective and H0 are correlated, we cannot go beyond 70, and that really means that the high multiple polarization data from Planck actually rules out this model as a solution to Hubble tension, because the tension remains more than 3 sigma. So in these plots, we have actually separated the two modes. What you can see in here for the NS part, as I said, that the strongly interacting mode prefers lower NS values, and this has implications for inflation models, as we will see later. So these are two-dimensional correlation plots, and as you can see from the top right contour plot, that N effective and H0 are strongly correlated. You can see it from the tilt of these contours, and you can see that since high values of N effective are disallowed when high multiple polarization data is included, it also disallows high values of H0. So so to summarize, log G effective is degenerate with theta MC and NS, and this allows for a bimodal posterior distribution even with the latest full Planck data. But with the full Planck data plus extra data, we found this 95% bounce where H0 is actually just 66.7 plus minus 2, and N effective is 2.7 plus minus 0.3 around. And so even if we were to reanalyze the data with fixed N effective of 3.044, one would likely get H0 values close to 6970. So this does not work as a solution to the Hubble tension. And even more importantly, this model does not work better than the non-interacting case, which actually produces H0 of 67.3 plus minus 2. So we also find from log likelihood calculations and from evidence ratio calculations that the strongly interacting mode is disfavored compared to the non-interacting case. And also, neutrino self-interactions are strongly constrained from particle physics experiments, with the exception of flavor-specific interaction among tau neutrinos. So given all that, we can say that with the current data, that strong neutrino self-interaction model does not look like a promising solution to the Hubble discrepancy. And if you just introduce the interaction among only tau neutrinos, then you have much lower effect on the CMB power spectrum. So that has even lower effect on the H0 value. So that really doesn't solve the Hubble tension, even if you include it only in the one neutrino sector. So the next part is related to the inflationary models, and this was also written with Steen Hannestad and Thomas Strom. So for inflationary models, we consider this tensor and scalar and tensor power spectra in the power law form, where AS and NS are the scalar amplitude and spectral index of the scalar perturbations, primordial scalar perturbations, and PT gives you the amplitude AT, and NT is the tensor spectral index. And we have this tensor to scalar ratio R as AT divided by AS. And a slow-roll single-field inflationary model will have this form of Lagrangian, which comes from basic scalar field theory, and it has now you can define this slow-roll parameters epsilon and eta in terms of the field, and after that you can define the cosmological observables NS and R based on these slow-roll parameters at the start of inflation. Inflation ends when epsilon it becomes equal to 1, and then you can define the number of e-folds between the start and the end. And so n star equal to 40 to 60 creates observable fluctuations in CMB, and based on a potential V phi and a choice of n star, one can predict the scalar spectral index and the tensor to scalar ratio R. So we are interested in natural inflation and Coleman-Weinberg inflation, which have the potential on the screen, and both models are ruled out by current cosmological data at much more than 2 sigma in the minimal Lambda-CDM plus R model, and that is why we are interested in this. So as you can see that these models are heavily disfavored when we consider the Lambda-CDM plus R model. The magenta lines are the predictions for the natural inflation in the 50 to 60 range for the number of e-foldings, and the black line gives you the prediction for R and NS for the Coleman-Weinberg inflation in the small field limit, where it has vanishingly small tensor to scalar ratio. And you can see both these models are ruled out in the Lambda-CDM plus R model. Now, when you go to not the non-interacting case, but with an effective and some of neutrino masses as varying parameters, then you see that with Planck and Weizsäcker, we do have agreement with the data, but when you include the extra data from Planck 2018 lensing plus BO plus RSD plus BO and RSD from BOS data release 2 and supernovae data from Pantheon, then you can see that these models are disfavored at more than 2. These inflationary models are disfavored at more than 2 sigma. But now, if you introduce interacting neutrinos, then you see that the allowed parameter space expands even more, because the interaction prefers lower NS values. And interestingly, you see that in the 3 neutrino interacting case, the strongly interacting mode is actually disfavored by the data. So the contour in NS is mostly in the NSR plane is mostly defined by the moderately interacting mode, whereas in the 1 neutrino interacting case, the strongly interacting mode is not disfavored by cosmological data compared to the non-interacting case. So in this case, both NS and in both the moderately and strongly interacting mode contribute to this NS allowed region, and so the 1 neutrino interacting case actually has slightly broader allowed region compared to the 3 neutrino interacting case. And what we see that both of these inflationary models are allowed at 2 sigma, but not at 1 sigma. So yeah, the reason to consider 1 neutrino interacting is, of course, because from particle physics experiments, only the interaction among tau neutrinos is still not completely ruled out. But that is only in the moderately interacting regime, and that is where this paper comes in, where we consider inflation models with non-minimal coupling. So what happens if inflation models have non-minimal coupling? Yeah, in this work, we only considered the moderately interacting mode in the 1 neutrino interacting scenario, because, as I said, particle physics experiments only allow that mode. So the strongly interacting mode, even in for interaction among tau neutrinos, is basically ruled out. So what we do in this model, in this work, is see how, if inflationary models have non-minimal coupling, then what coupling values will be accepted by the data. So here F phi defines the coupling to the gravity, and in a minimal coupling scenario, F phi would be just equal to 1. And so we consider two formulations. One is metric formulation, where Levi-Civita connection depends on the metric of the manifold, which is G mu nu, and there is also a Palatini formulation where the connection and the metric are described as independent variables. But these two connections, metric connection and the connection in the Palatini formalism, can be connected through this equation number 7, where omega phi is defined in terms of F phi. And if F phi is equal to 1, you can see omega phi would be 0. So basically, these two formalisms are same when in a minimal coupling scenario, but in the non-minimal coupling, they are different. So in natural inflation, we consider this F phi to be 1 plus xi phi square, whereas in the Coleman-Weinberg potential, we use this form of phi where xi, where you can have two situations where phi is greater than the vacuum expectation value and phi is less than the vacuum expectation value. Now, so for natural inflation, what we find that we studied particular values of xi, and what we found is that this minus 10 to the minus 2 this value is allowed by both Lambda-CDM and the one neutrino interacting model, but the other xi values are ruled out more than 2 sigma in both models. But of course, the one neutrino interacting model, since the parameter space is larger than the Lambda-CDM case, allowed parameter space is larger than the Lambda-CDM case, we see that it is disfavored only marginally, and the metric and Palatini formulations give almost similar results for the xi values as far as NSR predictions are concerned in the natural inflation model, because Palatini formulation differs predominantly when xi values are much more large. So for the Coleman-Weinberg potential in the metric formulation, we see for the phi greater than Vev case that this 10 to the power, xi value of 10 to the power minus 2 is allowed by the one neutrino interacting case, but it is disallowed by the Lambda-CDM case, whereas xi equal to 10 is allowed by both the models, but xi equal to 0 and a negative xi of 10 to the power minus 4, those are ruled out by both data sets with very large significance. On the other hand, for suitable potential and metric formalism for phi less than Vev, we see that all the negative xi values are actually allowed by both models, but in case of positive values of xi, some of them are allowed by the interacting scenario, but Lambda-CDM disfavors them at more than 2 sigma. For the Palatini formulation, we see similar results for the phi greater than Vev case, and here 10 to the xi equal to 10 to the minus 3 is allowed by the interacting scenario, but it is ruled out by Lambda-CDM, whereas the 10 to the minus 1, xi equal to 10 to the minus 1 case is allowed by both models, whereas other values are ruled out. Again, in the Palatini formulation, we see that for phi less than Vev, a similar situation, that the negative values of xi are accepted by both models, whereas the positive values are basically ruled out by the Lambda-CDM case, whereas they are allowed by the interacting scenario. So overall, we see some values of this non-minimal coupling can be accommodated by the interacting scenario, where they are disallowed by the Lambda-CDM case. Thank you, and please ask questions on this topic.